Driving in poor weather conditions continues to remain one of the most dangerous things for American drivers. The Department of Transportation states that due to low visibility conditions, we annually see over 38,000 car accidents leading to 600 deaths and 16,000 injuries. Current solutions to try and rectify this use ultrasonic sensors to measure the immediate area around a given person's vehicle, but this is limited in scope and application. We think using 5G computing and MAC processing, we can aggregate the data from a number of vehicles in a network in order to create an expanded representation of the road both ahead and behind of the given vehicle. This would allow the user to not only better predict upcoming road hazards, but also to be able to see when their vision is otherwise limited.
So in order to represent our solution, we created a mock environment which contains 4 different cars in the network along with 2 foreign objects. These cars in the network are represented by these blue dots, whereas foreign objects, which may be cars outside of the network or foreign objects that have fallen onto the road, such as trees or something that's fallen off the top of the car, are represented by red dots. Each car senses the different objects within their own vicinity using their own sensors and broadcasts this data to the MEC. This MEC then congregates the data into one graphical representation of the road. When it does this, it clusters together different close sensor values to represent a single object, along with removing any redundant values, such as when a car within the network senses another car in the network, seeing as this point would be redundant as we already know those vehicles are within the network. Now, once this data is congregated, the MEC then broadcasts back to each individual vehicle the locations of objects that may be significant to their driving experience. So, for example, with car 1, we can see the 2 objects that were in its near vicinity, but we also may be able to see an object significantly far away that was measured by other cars' sensors. This may be significant for a car that may not be able to be seen due to low visibility conditions, for example. And then we can also, for example, see objects that are coming up from behind, so drivers may be wary of somebody that may be approaching them while they're speeding or something like that, and so on and so forth for each individual car.
When considering the rollout of this technology, there are 2 primary limitations, which are the number of cars in the system, which requires consumer cooperation, and the MEC locations and distributions. To start, we could focus on major metropolitan areas or sections of highway intersection in order to try and maximize usability and expand as we see fit. Additionally, this technology has major benefits for potential autonomous or semi-autonomous driving, as the global MEC representation that we calculate could be used to estimate behaviors for each of the cars in the network.